Last episode, we built linear and logistic regression, the two atoms of supervised learning. Now, three more classics, SVMs, trees, and ensembles, turn that same mindset into decisions, starting with one question: where exactly should the boundary go? Picture two crowds and you have to paint a line between them on the ground. You could paint it hugging one crowd, but that's risky and one new person, and you're wrong. Better to paint it down the middle, as far from both crowds as you can. That widest possible gap is the margin, and maximizing it is the whole idea of a support vector machine. Of course, real data is messy. Some points wander into the gap or onto the wrong side, so we need a way to charge for that. Enter the hinge loss. If a point sits safely beyond the margin, it costs nothing, but the moment it crosses in, the cost climbs in a straight line. Trees take a different tack entirely. They ask yes or no questions and measure how much each question cleans up the mess. For the SVM, the hinge loss is max of 0 and 1 minus the margin, summed over points 0 when you're safe, growing linearly when you're not. For the tree, we score a split by information gain, the impurity before minus the weighted impurity after, where impurity is entropy or Gini. A perfect split drops impurity to 0. Gain equal to the whole thing. This math is everywhere. Max margin classifiers powered a decade of text and image classification before deep nets, and kernels let them bend around nonlinear data. Information gain is the engine inside every decision tree, and ensembles glue it together. Bagging, random forests, averages many trees to crush variance, while boosting, gradient boosting, stacks weak trees to chip away at bias. That's why these still top the leaderboards on tabular data. Here's the whole thing in one file. We'll score one SVM hyperplane's hinge loss on 6 points, then measure the information gain of a single tree split on the same data. We seed layout 6 two-dimensional points in two classes and label them plus and minus 1. We pick a candidate hyperplane, a weight vector and a bias, and compute each point's functional margin, label times distance to the line. The hinge loss is max of 0 and 1 minus margin per point. We sum it and count how many points violate the margin. Then we switch to trees. Entropy measures the label disorder, and we split the points on feature 1 at the value 4, computing the weighted child entropy. Information gain is parent entropy minus child entropy, here a full 1 bit, because the split perfectly separates the classes. So margins, impurity, and ensembling are the math under classical ML. Next episode we cross into neural networks, how stacking linear layers with nonlinearities and sharing weights as convolutions builds something far more flexible.